We're all good?
Yep.
So I have started with a little odd one out and common link quiz up on here. Hopefully everybody can see. If you have any ideas as to what the common link might be, could you shout them out? And especially who the odd one out might be, or what the odd one out might be, without dropping any hints. The main question will be why. So anybody got any ideas what the common link between these things up here might be? Go ahead. They are things in the periodic table. In fact, I have got some handy little helpers that will tell you exactly what they are. So we've got some salt, which is sodium chloride. We've got an iridium satellite here. We've got a neon sign.
A gold ring.
We've got Shane Long.
Aluminium foil.
We have an aluminium foil, train full of iron, and a gold ring. Okay, brilliant. But what's the actual common link between these elements? Yes, they're all just elements, they're in the periodic table, but what's the link between them?
They're all made of exploding stars.
Woo! Supernovae. So every one of the elements here is formed not in a star normally, not whilst a star is in the middle of its life, but is formed when a star dies, when a star explodes. And that is what I will refer to for the rest of the talk as a supernova. What's the odd one out? Shane Long. Why? Well, not only is he made from supernova dust, but he's also quite like a supernova in that he rose very quickly and then faded away pretty quickly as well. Okay, so that's a little intro. Hi, I'm Phil. I research exploding stars at the University of Southampton. Before that, I grew up in Gloucestershire. I studied at Durham University and then did a PhD in Munich, where I got fat drinking lots of beer. And now I've moved to Southampton. I started running a lot, and actually, a few weeks ago, I ran a marathon dressed as Miss Piggy. I was gonna say, if nobody believes it, there's me dressed as Miss Piggy. I got Princess, I got there is Peppa Pig shouted at me, all sorts of things. So, okay, so I'm gonna ask three main questions this evening. The first one is, how do we find a supernova? Because we can't really just like go look in the sky when it's light and cloudy like this and just find them. We have to use some special techniques to find exploding stars. How do we know what one is? And to be honest, why do we care? Why do we care what a supernova is and how it explodes? Okay, so the first one, how do we find a star at the moment it explodes? Most people, if you think the word supernova, if you Google supernova, you will find a picture that looks a little bit like this, right? A nice artistic impression of a star going bang. Actually, that's not quite what it looks like. Spoiler alert. The background here, that's actually what a supernova looks like a few million years after it's exploded. So, not quite what we're looking for if we want to catch one as it's going bang. So, that's out. How do we do it? Well, supernova happen as stars die. Stars live in massive groups called galaxies. We have maybe 100 billion stars in our own galaxy, the Milky Way. So if we're going to find a supernova, why not look at some galaxies? Unfortunately, supernovae are quite rare. One happens in the Milky Way maybe once every 100 years. So if we just look around our own galaxy, we're probably not going to see one on any given night because we might be waiting 100 years. So why don't we look at some other galaxies? Right, brilliant. So which ones do we look at? Well, find some nearby ones because they're bright, look at them, go back 3 weeks later, look at them again, and see if they've changed. If a star's exploding, it's probably going to get brighter. That's what a supernova is. Goes up, comes down again. So Go back 3 weeks later, and if the picture of that galaxy has changed, then maybe we found one. So here's an example from back in 1995. So we're staring at a little fuzzy screen, and there's a little fuzzy blob, and that's a galaxy. And we go back 3 weeks later, and we look at the fuzzy blob again. Does it look like it's changed? No? Well, if you use some computer software and subtract that image from that image, there's a big black dot in the middle. That's a supernova. So the galaxy is brighter, and the reason for that is that a star there has exploded. This was some billions of kilometers and light years and whatever away. Brian Coxey numbers added on, zeros and zeros. Annoyingly, there are things like this. That's a really bright star in our own galaxy in the foreground, and when you try to subtract it, the computer gets confused. So if you run all of the computer algorithms to detect little fuzzy blob supernovae, you actually just end up getting thrown at you annoying bright stars. So we have to clean them out somehow. Okay, great. So you can find these, but staring at galaxies to find supernovae is actually not very efficient at all, because, as I said before, you don't know when one will explode in any given galaxy. So you could be staring at this one for 100 years before one explodes. So I will move to a survey that I'm part of and that Southampton has a real big stake in, called the Dark Energy Survey. This is a survey based in the wonderful country of Chile. We've actually just sent a couple of people over there, like yesterday, to go observing. How do you go about finding supernova in a modern survey? You get a massive telescope, like that one. It's got a mirror which is 4 meters across, so kind of from me to Sam and Thomas over there. That's just the size of the mirror in the telescope. Great. You get a really big camera, in fact, potentially one of the biggest cameras ever made. That's 513 megapixels, so quite a lot of iPhones, and quite a lot more expensive. And that can point at an area on the sky like about the size of 3 full moons across. So compared to like any given telescope where you normally can just see a tiny little part of the sky, it's got a really wide view. And that means we're not looking at individual galaxies, all these little fuzzy points of light. We're looking at a massive part of the sky, and so we can catch any supernova that goes off in any of those galaxies. We don't have to pick which ones to stare at. Okay, great. So, as you can imagine, maybe we might point our dark energy camera at a nice big spiral galaxy like this. And if you look here, nothing. And then if you look here, boom, we've got a supernova. Yeah, shall we do that but in video? Okay. Where do you think the supernova is going to happen in this galaxy? Middle? Bottom? Top? Up there? We'll press play, hopefully. Not in the big galaxy. Not in any of these quite bright things. Zoom into a little fuzz, and then that's what we're actually looking for. So when I tell people out in the pub, what do you research? Oh, I look for exploding stars out in the universe. That's actually what I look at. Except normally we don't do it in color, it's normally just in black and white. Okay, let's play a game. So the Dark Energy Survey was up for 5 years, so each one of these is a year, and we just have date along the bottom, and we have brightness along the top. And these are 3 separate points in like that part of the sky. Which one of these has a supernova, and where is it? So this is just brightness against time. Who can see the supernova? Top. Anyone for top? Anyone for bottom? Anyone for middle? There it is. But actually, that was a bit of a cheat from me because we don't actually know what that one is at all. It doesn't look like any supernova that we've ever come across before. And a colleague of mine, Mika Persiainen, is currently writing a paper to be submitted soon talking about this exact event and trying to work out what it could be. But we actually currently have a sweepstake on our office whiteboard saying, what are they? Some of us think it's something like neutron stars and black holes colliding. Some of us think it's big stars losing their outer gas envelopes. No one really knows. So ask an astronomer, what's a supernova? Actually, do we really know? Okay, but for most of them, we can go and find out what they are, what is happening, why the star's exploding, and how it's exploding. And the way we do that, little hint, is we take spectra. So we basically just put a prism in front of our telescope, split all the light up into the different wavelengths, all the way from kind of the ultraviolet and the blue through to the red, and see how bright different parts are of the spectrum, how the brightness changes with wavelength. So maybe a little bit like this. Oh, it's blue and there's no contrast. Can anybody see this?
Yeah.
Okay, good. Does this look like a supernova spectrum? Actually, no, that is what you would get as a spectrum if you pointed the spectrograph at the blue sky. That's a spectrum of the sky. So if we say red is here, infrared, maybe ultraviolet is over here, then the spectrum goes up and it's brightest kind of leaning towards the blue side. So that's why kind of the evidence that the sky is indeed blue. But what you might also see in here are some little features. Like it goes up and down, there are absorption dips and little emission peaks. So it's not just nice and constant, but there's bits and bobs. And those come from different elements and different molecules in our atmosphere. So there are some handy labels which are done in scientific terminology and they mean nothing. So calcium, for some reason we've called H and K. We do have water as H2O here, so different wavelengths will have different absorption lines from different elements and molecules based on the atomic transitions that happen in those elements and molecules. And that's really helpful because we can then determine the composition of the atmosphere. Well, we can do exactly the same with a supernova, except it's not quite as high signal. So this was our beautiful spectrum of the blue sky. This is our spectrum of a supernova. So instead of being really full of signal and really nice defined features, we basically have a lot of noise, and there are some wiggles that might be due to certain elements. So, well, we kind of know what the intrinsic spectrum of a supernova should look like. It's what we call a black body, because it's just an expanding ball of fire, basically. So it emits, and it's quite blue because it's really, really hot. So it actually emits mostly in the blue, the ultraviolet, and then is a bit fainter in the red. But there are actually a lot of absorption lines. And we know, thanks to people who have worked in the laboratory and with pen and paper, exactly what wavelength we expect the absorption lines to be at. So when we see them in the spectrum, we can match them up to the elements that we see. So for example, this big one here is silicon. And then we have sulfur, and there's also iron, and magnesium, and calcium, and in fact, all of the little ones will be from different elements as well. And because if we look at maybe 1,000 supernova, we'll find that maybe 500 or 600 all have these exact same elements. We put them into different classes. We're very imaginative as astronomers. So these ones we call type 1A. There's also type 1B, type 1C, type 2. and many, many subclasses, and if you talk to some people in the department, they will be able to tell you each and every supernova and each and every class, and it gets very, very confusing. Okay, so moving on to the final bit, which is why I care. Well, we can start to see here, maybe, why supernova might be important, and we also, from the starter problem of odd one out, maybe why certain elements and supernova might be important for life and for humanity. But we'll take a little detour, so I hope the sound works. This should be a train going past, and listen to the sound because it will be the kind of well-known Doppler effect.
Use the microphone maybe, close to the laptop.
Again. How is it? Right, one more time. Right. So, when something is travelling at speed, sound waves from it get compressed when they're coming towards you, so the pitch sounds higher. And then when it's moving away, they get dragged longer, so the pitch goes lower. It's called the Doppler effect. Exactly the same thing happens with light if you're moving fast enough. So, when a supernova has exploded and all of this material has been thrown out into outer space, it's moving very fast, and the light that's emitted by it gets Doppler shifted. The stuff that's moving towards us gets shifted slightly bluewards, and the stuff moving away from us gets shifted slightly redwards. And therefore, the faster the things are moving, the wider these absorption lines are, because stuff is getting shifted further into the blue and further into the red. So actually, by measuring the width of these lines in terms of wavelength, we can measure the speed that the ejector has been thrown out into outer space and the speed the supernova is expanding at. Does anyone want to have a guess? We've got another speed thing here. How fast the supernova is expanding into outer space? Shout some numbers.
0.5 C.
0.5 C? Not quite. Not quite. Miles an hour? Anyone?
Oh, 500,000 meters per second. I can't do miles.
Yeah, so about 10,000 kilometers per second. Yeah, or 22 million miles an hour, or 16,000 times faster than Concorde. I didn't use London buses because they go really, really slow. So about 16,000 times faster than Concorde, or, come on, that many Concorde, no. That many Concordes. It's so many Concordes that PowerPoint can't even handle it. So, why do I care why these elements are being thrown so fast out into outer space? Well, that speed is so high that silicon and iron and calcium, they're not just being ejected from the star, they're not just being ejected from their local cluster of stars, they're being thrown right across the entire galaxy. In fact, some of them are even being ejected so fast that they can leave the galaxy altogether, move around in the middle of nowhere, and then fall back onto the galaxy a bit further on. Right? And this is one of the only processes that can do this at all in the universe. So, if you've got a little star forming, like the sun, and there's some planets forming around it, and you want to have some heavy elements like iron and calcium and silicon in your new planet that you want to form life from, well, you needed supernova to get those elements there in the first place from other parts of the galaxy. So if it wasn't for supernova, we wouldn't even have our heavy elements, our radioactive elements we were talking about earlier, we wouldn't even have them here. So why do I care about supernova? Well, they're kind of really, really important as to why we're here at all in the first place. Thank you.
And thanks to Phil for a brilliant talk. So does anyone have any questions for Phil about supernovae, trains, tutus, anything?
What's the difference in intensity with the blue sky and the supernova sky? Because you had a line showing intensity, but I don't know what relative.
Okay, so the blue sky is like pretty bright because it lights up the world even when the sun's not in. So I did have a fact, and we can kind of do some little mental maths to get there. So the sun is about a magnitude of -26 in our weird astronomical magnitude system. And each 5 magnitudes is a factor of 100. So the faintest stars that we can see in the sky at all, and magnitudes go up when you get fainter, are magnitude 6. So that's a difference of 32. So we've got about 100 to the power of 6, which is many, many millions. The supernova was a magnitude of 24. So we've got another difference of about 18. So we're talking 10 with about 12 or 13 zeros difference in intensity between the night sky, or between the blue sky and between the supernova. So if you took the faintest star you can see with your eyes in the sky and put that as like a candle at the end of the room, you could just about see that candle glowing, like the embers of the candle glowing. The supernova brightness would be like moving that candle to Alaska and still being able to see it with the telescope we have.
So do we have any other questions for Phil? Anyone?
How much mass have you thrown out?
So in a supernova like this, the spectrum I showed was a type 1a. That's a white dwarf exploding, which is about the mass of the sun exploding. The amount of stuff that gets kicked out in total will be some fraction of like 0.3, 0.4 masses of the sun that get kicked out.
Very small amounts then.
So it's, yeah, compared to the size of the star in the first place, it's like a below half fraction of that. As you get to bigger and bigger stars exploding, the fractions stay similar, but that means the total mass kicked out is more.
Do we have any other questions, Phil? Any more? No? Okay, there. Oh.
Okay, so if, say our sun, you said like when they explode, elements can go outside the galaxy. Say our sun slowly, would it go outside our galaxy? The southern side?
Yeah, so the kicking out of the galaxy kind of happens when you have multiple supernovae going off. I say at the same time in the same area. That means within like millions of years of each other and within millions of light years of each other. So together they can start kicking stuff out. So the sun on its own probably, well, the sun on its own disappointingly won't explode as a supernova. It's too small. If it could, then we are far enough outside, like away from the center of our galaxy, that it could start kicking it like significant distances away. Yeah. And we actually had some measurements taken on the seabed, so moving back to the sediments that we were talking about in the first talk, that showed that about 5 million years ago, there were 4 or 5 supernovae very close together in time that pushed a bubble of like ejecta all together through our solar system, and that may well have ended way outside the galaxy.
Right, and any more questions, Phil? Anybody more questions about supernova? Oh, we do.
Sorry. Do you have a favourite supernova?
Do I have a favourite one?
Yeah, favourite blur.
So, the one I showed you is kind of it's my favourite maybe supernova. It has a really exciting name of DES 16E2BJY. However, there was one that we had last year, and so we give them names purely by when they appear in the year, and then you add letters on, like just the next letter, whatever. Last year we had supernova 2018 cow. So we've just been calling it the cow for the last year, and all the puns have been milked, and etc., etc., etc. Right? So I think we kind of have to say the cow is our favourite supernova. They actually, the algorithms that make the names, someone has programmed them to miss swear words as well.
Great, and we have time for one more question. No? Okay, well in that case, can we have another round of applause for Phil?